So, the last lecture we have discussed about this boundary condition. Now, we will move from here. So, two types of boundary condition that we have discussed, one is the Dirichlet and the Neumann. Now, we will see how you find out the accuracy level, because that is one of the important criteria. So, what you are trying to get is that if you have a, let us say, element like this, which is center C and the coordinate is x c, and you are moving to a point which is called x. So, function would be phi x, and you have all these connecting faces sitting there. Okay. So, you have all the terms, since it is a element C, you have phi C, delta phi C, you have delta delta phi C, all these are there. So, what you can see phi x, which could be phi C plus x minus x c dot delta phi C, where your phi C is phi x c. Okay. How do you get the spatial variation? So, first you look at the spatial variation. First you look at the spatial variation, that means it is again it would be similar kind of, or rather same Taylor series, but we will now write it explicitly, phi x equals to phi C plus x minus x c dot delta phi C, okay, plus x minus x c square 2 double dot del phi C plus 1 by 3 factorial x minus x c cube del phi C plus so on, and you can have x minus x c to the power n So, this would be multiplied of n minus 1 times del phi, and this would be n times. Okay. So, x minus x c is the essentially the distance vector between these two points, and if you look at this del c, del triple del c, this will retain the second derivative, third derivative, nth derivative, like that. Okay. Now, this is how you express your spatial variation, getting or given a value at centroid C. Now, mean value, if you do mean value approximation, what is that? So, I am calculating phi C bar, which will be nothing but my V C integration of V C phi dV. So, that I can write 1 by V C phi C plus x minus x c dot delta phi C plus order of x minus x c square dV. Okay. So, if you write phi C by V C dV plus 1 by V C x minus x c dot delta phi C dV plus 1 by Vc, you see order of x minus xc square dV. So, essentially if you look at it, it turns out to be the mean value approximation is phi c plus order of x minus xc square. So, that means the mean value approximation what you get, this is a very important term which is your second order accurate. Now, this would be a very important calculation to have, because when you calculate the other derivatives and other terms in the explicitly in finite volume formulation. So, you can estimate the order of accuracy and all this. Now, similarly, you can have the fluxes, okay. Let us say convective fluxes approximated and see the order of convective flux. So, you just take this side of the element and this is the C, this is the face F. So, this is F. So, Jf dot Sf is rho V phi dot Sf. So, that my convective flux, okay, and my diffusive flux would be minus gamma del phi f dot Sf. So, that is my diffusive flux. So, these are two components. Now, if you look at the convective flux, okay. So, the convective flux you have rho Vf dot Sf phi f. So, essentially this is the integration of f rho V phi dot ds, okay. Rather you write the rho f Vf phi f plus x minus xf dot delta phi f plus order of x minus xf square dot ds. And then if you segregate this out, you write rho f Vf phi f dot f ds plus integration x minus xf dot delta phi f rho f Vf dot ds plus f order of x minus. So, essentially in a Taylor series expansion you just retain one or two term initially and then truncated the higher order term. So, this will actually get you back rho f Vf dot Sf phi f plus order of x minus xf square. So, again if you look at the higher order term sitting here, this is second order accurate. So, what you got once you calculate the mean value at the cell center, so that also second order accurate. Once you calculate the convective flux, that becomes second order accurate. Now, you can look at the diffusive flux. So, what accuracy it possesses. So, the diffusive flux you have f gamma delta phi dot ds. So, you can write over this surface gamma delta phi f plus x minus x f dot delta gamma delta phi plus x minus x f square dot ds. You collect the term on the right hand side. So, the first term will get you back the gamma del phi f dot f ds plus f x minus x f ds dot product of the tensor delta gamma delta phi plus order of x minus x f square. Okay. So, if you collect, so this will be gamma delta phi f dot s f plus order of square. Okay. Again the higher order term sitting here is the second order accurate. So, that means if you use this particular approach and discretize the system. So, essentially the generic finite volume discretization gives you back all the convective diffusive terms are of the second order accurate. One can always achieve higher order accuracy. So, that case higher order approximation you have to use. So, if you want to do that, so you can get this integration of phi ds with some sort of a weighting function like this. So, you can achieve higher order system, but in general all the finite volume discretization return you back the second order accurate system, which is handy to work with the generic finite volume system, but one can always achieve the higher order system with this kind of a approximation. This get you an idea about the steady state system. Now, if you move to the transient system, so what happens to the transient equation? Okay. So, the transient equation you integrate over now time along with space. So, your unsteady term will be integrated over a small interval of delta t, and this term now will be retained, the unsteady term, and the other term will be also integrated over the time. So, these are my convective fluxes. Okay, minus T plus delta T, I will get diffusive fluxes gamma delta phi f dot ds. So, you get Now, along with the spatial variation, you get the integration done over temporal variation also. Now, this term previously we have dropped out. Now, this is the unsteady term or the term which will be retained, and this should be equals to your generic source term. So, if you compare between the steady state and the transient system, except this particular term and the integration over time, if you drop out, everything else has been integrated and you obtained a linear system for the steady state system. So, now when you move to the transient system, now you have a integration over time. So, now you have to simplify each term. So, first you look at the unsteady term, what happens to that. Okay. So, once you do that integration of the unsteady term, so that get you back the integration of so that is essentially the integration over the time interval t plus del t rho phi by del t V c dt. Now, we have already seen the mean value approximation for this. So, this is nothing but rho phi dV, which we can write second order accurate system. So, that is the mean value approximation that we have seen. So, if I put this back, what I will get? I will get the integration over time with the first term sitting there B c dt plus integration over time summation of the convective fluxes f rho v phi dt minus the diffusive fluxes f gamma del phi dt equals to the time integration of the source term. Okay. So, each term now retains the integration of dt and you get the integrated system like this. So, the whole objective here is that from this system. So, if you recall, this is a kind of element we are dealing with. I mean, it could be something else and it has some surroundings cells. So, these are F1, F2, F3, F4, F5. So, it could be 4 phases, 6 phases, does not matter. Now, essentially all this integration is done over an element, and then from here you get back the linear system, and from the linear system you finally solve the problem of the linear equation. Now, using some midpoint rule you put it back. So, using the midpoint rule, you get this equation now, t plus delta t del t rho phi V c dt plus t plus delta t. So, it gets summation of phases rho v phi minus t plus delta t equals to so you get a simplified system. Now, from here you can always get the algebraic expression which will lead to the system of linearized equation. Now, there are certain things for your numerical method should have. One of the, or rather some important properties of discretized equation. Okay. So, what we are doing here, we have PDEs. Now, PDEs are discretized to get linear system. Okay. Now, this discretization process you must have, and this is where we have applied our numerical technique of finite volume method. Now, one of the important property that we have also discussed about the conservation. Okay. That means all the conservative quantities like mass, energy, etc., they must be conserved even after discretization. So, what is important here is that we start with our mass equation, energy equation, I mean basically momentum equation, energy equation, continuity equation, all these conservative properties like mass, energy, all these things, they must be conserved in the discretized equation. You cannot afford to lose the conservation property. So, this is one of the very important or fundamental property of this. Second is obviously, so first thing one has to make sure that the physical properties or conservative properties are properly conserved when you move from the differential equation to the discretized equation. So, they cannot be afford to lose any conservative property. Second important property that comes out to be the accuracy. Okay. So, this is again the, it essentially refers how close a numerical solution is to the exact solution. So, this is where actually you come down to the accuracy of the system, and in one or two lectures before we have talked about the accuracy and how do you achieve, and just right now you have also seen how one can actually get the, and this essentially means that order of truncation error. Okay. And we have seen that when you do finite volume discretization, all your mean value, convective flux, diffusive flux, everything is of second order. So, the higher order term in the truncation expression or truncated expression will lead to the accuracy of the system. Okay. So, more and more order is, the higher order term is retained in the expression, you get higher order expression for your numerical scheme. So, at the other time also one can increase the accuracy by reducing the grid spacing. So, since these are leading order term would be of some delta square, delta cube or something, if you have a small delta or the grid spacing is less, so this will reduce the reduce the error and you can increase the accuracy. So, third is that, so this is where the accuracy is essentially has to do with how you have discretized your partial differential equations and what kind of approximation you have made. So, the approximation made and the leading order term that are kind of truncated off from your Taylor series expression will lead to the third important property is the convergence. So, that is again has to do with the solution algorithm or process. So, one may say my solution has converged. So, that means when you do some physical iterations and the error between the process or the values they are not changing, one can argue that solution has converged. So, sometimes it is also used for the transient calculation when people say the solution yet not converged for the time discretization. So, it has to do with both spatial convergence and spatial and temporal convergence. Okay. So, this is how one can talk about the convergence. Now, fourth property which is again going to be very important is the consistency of the system. Consistency of the system. So, that essentially when you approximate your PDEs to a algebraic equation. So, this is the approximation. When you do that, how consistent it is? It essentially at each point in the solution domain, the numerical solution approaches towards exact solution. So, that essentially means that whatever you have the discretized error that approaches to 0, and the discretization error comes from essentially the primarily the truncation error and also the some sort of a numerical errors, round of errors. Now, fifth property which is also very important is the stability. Okay. So, the stability is that something when you talk, it is the characteristics of your discretized equation. Okay. So, this has to do with the stability. That means, it is a very inherent property of your discretized system, how you can say when, because the discretized systems only will finally take you to the solution. So, the path of the solution is be important, and that can dictate whether the solution is stable or not. So, it has to do with both the discretized systems and the solution process. Now, another property is that your scheme and all these process should be also cost effective. That means, I should have some algorithm or code that must be economical. That means, here economical does not mean in terms of money, I mean it directly not in terms of money, it essentially in terms of the computational overhead. That means, how much computational cost is associated with this particular algorithm or the code that you have obtained. And how do you have obtained that? You have the PDEs, you discretize the PDEs, get a linear system, you have a linear solver, and when everything is actually put together through a programming language and you get either a sequential or parallelized version of your code, that is when you use that particular code to solve a problem, you can actually estimate whether it is cost effective or not, because it depends how much time it takes to do the calculation. Thank you.